All right, let's just jump right in. You've probably seen the headlines, right? An AI mastering the unbelievably complex game of Go, or completely demolishing classic Atari games way faster than any human could. But how? How does that even happen? It's definitely not just about number crunching.
That's the thing. They don't just calculate, they learn. And they learn in a way that's, well, kind of like us, through trial and error. Trying stuff, messing up, and getting feedback. This whole powerful idea is called reinforcement learning. And honestly, it's one of the most human-like ways we've ever taught a machine to think.
So take something like DeepMind's AlphaGo. The creators didn't sit there and program in all the rules for what makes a good move in Go. No way. Instead, they just let it play against itself, literally millions and millions of times. It just kept trying things, failing, and then ping, getting a little reward every time it won. And that process, that's the absolute heart of reinforcement learning. Okay, to really get this, let's just forget about computers for a minute. Let's think about something way simpler, something you've probably seen before. Training a dog. I promise, the core logic is exactly the same. So first up, you've got your learner. In the fancy AI world, we call this the agent. In our little story, it's the dog. And the important thing here is it starts out as a total blank slate. It has absolutely no idea what it's supposed to do. Okay, so this agent, our dog, exists somewhere, right? We call that place the environment. For the dog, that's the living room. For an AI, the environment could be anything. A video game world, the chaos of the stock market, or even the actual physical world for a self-driving robot. And inside this environment, our agent can do stuff. It can take an action. So our dog might decide to sit down, or bark, or maybe jump up on the sofa. Those are all the moves it has in its playbook. Now listen up, because this is the most important part. When the dog finally does the thing we want it to do, like sit, we give it a treat. That's a positive reward. And if it does something we don't like, it gets zip, nothing. That simple feedback, that little treat, is the only thing guiding its learning. So the agent's one and only mission in life, get as many treats as possible. That's it. After trying things thousands of times, it starts to build this internal strategy. We call it a policy. And you can just think of it as a little mental map that says, hey, when I'm in this situation, sitting gets me a treat. So yeah, I'm gonna do that. Okay, so that's the dog analogy. Pretty simple, right? A dog learns to sit to get a treat. But how in the world does that idea translate from a living room into a computer chip? Let's pop the hood and see how this simple concept becomes something incredibly powerful. We're gonna look under the hood using the classic video game Pong. It's just the perfect, simple playground to see how an AI brain actually works. Okay, so in the world of Pong, what's the state? It's just where the ball and the paddle are right now. Simple. And the action? Even simpler. Move the paddle up or move it down. And the reward? A sweet, sweet +1 point every single time it scores. That's the treat. This brings us to a really key idea called the Q value. Now, this is basically the heart of the AI's decision-making process. Just think of it like an internal score. For any situation it's in, the AI gives a score, a Q value, to every possible move it could make. And that score is its best guess at how many future points it's going to get if it makes that move. So what the AI does is build this giant mental scorecard. We call it a Q table. It looks kind of like this. If the ball is high up on the screen, maybe the score for moving the paddle up is, say, +50, and the score for moving down is -20. So here's the magic. The AI just looks at its table, finds where it is right now, and picks the move with the highest score. That's it. It's really that simple. But hang on a second. If the AI only ever does what its table says is best, how does it ever discover something that might be even better? This right here is a huge challenge in all kinds of learning, not just for machines, but for us too. And that brings us to this classic dilemma. On one side, you have exploitation. That's just sticking to what you know works, right? Playing it safe to get that guaranteed reward. But on the other side, you have exploration. This is about trying something totally new, maybe even random. Sure, it might not work at all, but it could also lead to you discovering some kind of massive jackpot, a brilliant new strategy you never would have found otherwise. I mean, think about it. It's a question you and I face all the time. You go to your favorite restaurant. Do you order the usual, the dish you know you love, or do you risk it and try something new that could be incredible or, just awful? So, what should the AI do? Well, the smartest strategy is a balance of both. To really become a master at something, the AI can't just be greedy and always take the known reward. It has to be curious. So every once in a while, it'll actually ignore its own scorecard and just try something random, just to see what happens. And it's that curiosity that lets it stumble upon strategies that even the best human players might have never thought of. Okay, so this whole idea of learning from experience, it's obviously not just for beating video games. This is already being used to tackle some of the most complex problems we have in the real world. For example, in robotics, this is how you teach a robot arm to learn how to grab some weirdly shaped object it's never seen before. In finance, AI algorithms use this to figure out trading strategies to get the best possible returns. And of course, with self-driving cars, it's all about learning the best way to drive by getting rewarded for being safe and efficient. So really, the next time you see an AI do something that just seems incredibly smart, remember our dog. Because no matter how complicated the problem is, at its very core, it's just a digital dog trying to maximize its treats. This is what's so powerful. It gives machines a way to master incredibly complex things all on their own, just from experience, without a human telling them exactly what to do. And that, well, it leaves us with a really fascinating question. Now that they have this new power to learn, what are the next great challenges we should ask our machines to solve?